Thank you for this opportunity. My pleasure and honor to welcome Professor Anurag Garg to this award function. On behalf of Professor Shubhankar Karmakar, our head, I offer our congratulations to him and also his research group for the accomplishments that he's being honored for today. Professor Anurag is in our Department of Environmental Science and Engineering, and he's also a visiting professor in School of Water, Energy and Environment at Cranfield University in the United Kingdom. Professor Garg completed his bachelor's in civil engineering from University of Roorkee, now IIT Roorkee, and then also his PhD from IIT Roorkee in environmental engineering in 2005. After completing his PhD, he worked at Cranfield University as a research officer for about 2 years before joining IIT Bombay in our department in the year 2007. His main research contributions include development of treatment schemes for sewage sludge to improve resource recovery, which is the focus of this presentation today. Decentralized composting system for wet biodegradable fraction of municipal solid waste, and also laboratory demonstration of high performance of the wet oxidation system for distillery wastewater. Professor Garg has more than 150 publications on solid waste management, wastewater treatment in international and national journals, conference proceedings, and books. Professor Garg has also been serving as an expert member on technical committees formed by government agencies. So with that, as a brief introduction, I request you to please join me in welcoming Professor Anurag Garg for his presentation. Thank you.
Yeah, thank you very much, Professor Sethi, for your nice presentation, for your nice introduction. So now, and I would also like to say thanks to IRCC and jury members for giving me this award. This is a very encouraging and motivating award for me. So today's presentation is actually on the recovery of value-added materials from sewage sludge. So I will just put it on the slide.
Yeah. Professor Garg, please take care of time because we are running behind schedule 15 minutes almost.
Yeah. So the title of the talk is Recovery of Value-Added Materials from Sewage Sludge. So this is the outline of my presentation. I am giving a brief background and then I will be presenting two studies actually, so which we have conducted on sewage sludge. So first is conversion of sewage sludge in adsorbent and its application in wastewater treatment. The second one is the performance of hydrothermal pre-treatment to improve resource recovery opportunities, and then I will summarize. So in these papers, actually, we try to focus on the sewage sludge management, so which is a byproduct actually produced from any sewage treatment plant. And its disposal is one of the major challenges before to all the municipalities, and it is also worldwide. It has been a big problem to dispose it in a environmental friendly manner. So land disposal and anaerobic digestion, these are the two major disposal methods for the sewage sludge, so which are often not very effective. So anaerobic digestion, generally it is not very effective because it has a large amount of particulates, and then solubilization, it becomes the rate limiting step during this process. So hence we have to actually find out a sustainable and efficient method for the disposal of sewage sludge. So among various alternatives, actually we focused on two methods. So one is we converted this into adsorbent, and this is because it is a carbonic material, so it is carbon rich material, so it can be actually replaced. It can easily replace the activated carbon which is produced from natural resources, and its utilization in wastewater treatment. And the second one is we are pre-treating this by one of the methods which is called hydrothermal method, because sewage sludge itself contains large amount of moisture content, so we need not to add any water from externally. So it doesn't require, this process doesn't require any water, and then we can, after pre-treatment, we can separate out the solid and liquid phases, and then we can utilize these different phases for further resource recovery. Now, this is a very basic information about this sludge generation. So here in this wastewater treatment plant, this is like sewage treatment plant, approximately 2500 to 3500 of the liters of this sludge is generated, which contains only 3 to 7% of solids. And secondary, it is biological sludge generated after biological treatment. Primary sludge is basically which is generated after sedimentation tank. So we allow the wastewater to settle down actually in one tank, in large tank, and the impurities, suspended impurities, they get settled down. And advanced treatment, it depends upon the intention of wastewater disposal after treatment. So sometimes we are going for nitrification, denitrification, which can be biological process, or we are going for some phosphorus removal, so which can be actually coagulation, flocculation process. So it can be chemical process or it can be biological process. Here you can see that the total solids concentration is different in all type of sludges. So this is 3 to 7%. So we can understand that this is, though it is sludge, but it is still a kind of a highly concentrated wastewater. And it is the dry biosolids concentration, and it is very difficult to dispose actually. So municipalities are facing a lot of challenge, as I told in the beginning. And the total solids generated from various processes contains high organic concentration and need safe disposal. So I am talking about first study. So where we converted sewage sludge into an adsorbent and we used it for the wastewater treatment. So it is a schematic diagram. So we got sewage sludge. So primary sludge also we got, and as well as we got secondary sludge from a running plant. And then we dried it. It is actually, it is dried material that is shown here, but we activated this with ZnCl2. So we used chemical activation process for this, and different ratios were used for sewage sludge to ZnCl2. And then we optimized all these conditions. So I am just showing like what were the best conditions that we obtained. So this is either of these two are actually found to be good, and then followed by carbonization in the absence of air to remove any volatile matters. And then after this, the material after carbonization, it is washed with acid and distilled water, so to remove any salts and any other impurities from the pores. And then the material was oven dried, and this is the sewage sludge. This is sewage sludge dried activated carbon, and its BET surface area that was quite high. It is from 500 to 628 meter square per gram. So we prepared different types of activated carbon. So this is the area that is actually varied. And we, in the recent study, we also tried to recycle the wastewater which was produced during this process. So wastewater one, it was subjected to chemical treatment, and we tried to recover zinc oxide. And in the second so where actually washing operation, again wastewater 2 was generated, so which was less polluted, and we tried to recycle it back. So in that manner, we were trying to reduce the need for fresh water also in the synthesis process. So this is the summary table which is showing the characteristics of various adsorbents. So this is the primary sludge. PS stands for primary sewage sludge. AS stands for activated sewage sludge or secondary sewage sludge, and GAC is granular activated carbon. So we prepared, so these are different sewage sludge to ZnCl2 ratios, and CAC stands for activated carbon, which was purchased from the market. So it is actually the peat derived activated carbon, and these were their BET surface area and pore volume and particle size range. So we can see that the BET surface area was comparable to the commercially available activated carbon, and this is the granular activated carbon, because granular activated carbon is normally used in the continuous studies. So therefore we also synthesize that. So this is from the activated sludge. Now this is some results that we obtained. So that is actually we used ciprofloxacin, which is one of the antibiotic which is used widely actually, and it is found in the wastewater. So we used in the synthetic wastewater solution where this concentration was 100 mg per liter, and it was done at the neutral pH. And we used adsorbent dose of 2 gram per liter, and then we can see. So we should note here that the performance of this waste-derived activated carbon samples was same as that of the commercially available activated carbon. So we can see this QT, it is actually the adsorption capacity. So that was around 30, this is milligram per gram of activated carbon. So that could be adsorbed. Now in the second study, what we try to do, we try to prepare this catalyst. So this is, we can say it Fenton-like catalyst. So where it is a heterogeneous catalyst where we used activated waste-derived activated carbon as the support, and it was iron was impregnated on this. And then we initial stage, we did only the adsorption process, and then we added hydrogen peroxide there. After this addition of hydrogen peroxide, we could get significant removal in the CPX concentration from the wastewater. And actually I am not showing here, this is total organic carbon, which actually tells us that how much carbon is actually removed from the wastewater. So otherwise in this process, what may happen that this ciprofloxacin, it is converting into some intermediates. So it's still carbon is present there. So TOC removal here, it was almost 60 to 70% when we actually used this adsorption followed by Fenton-like process, oxidation process. And this, for this particular process here, we reduced its pH to 3, which is the requirement. So all these conditions were optimized by using design of experiments strategy. Now, this is the another study that we actually did in the continuous reactor. So it's a very small continuous reactor where we varied several parameters. So we used different concentration of the antibiotic. So this is 20 to 100 mg per liter, and badite was 8 centimeter, and this is the flow rate was also changed. So here we saw the effect of the flow rate. So this is with the activated carbon derived, activated granular activated carbon derived from activated sludge. So here we can see again that with increase in the flow rate, then this is the time that is actually equilibrium time. So that is reduced. So saturation here, it is reaching to the saturation, and then it will increase the concentration of CPX in the outlet very fast. So that is the time, like 2 hours is suitable when we are operating the system at higher flow rate. And when it is at lower flow rate, then we can use it for longer period. The column can be used for longer period, approximately for 4 hours. So we saw this effect of various parameters on the adsorption. So here we can see this is the with the commercially available granular activated carbon. So if you will notice that even at the 1.5 milliliter per minute, the activated carbon, it was started actually exhausting even after 2 hours. So here we can say that still our performance of our this waste derived activated carbon was quite comparable or even better actually, if we see that. So this is one of the applications. So wastewater, it can be used because it is a waste derived material. So we cannot suggest it to use for the water treatment. Rather, it should be used for wastewater treatment. And in wastewater treatment, because now the standards have become very strict. So we have to treat the wastewater to higher levels. And then adsorption is one of the most effective polishing treatment method for the removal of recalcitrant pollutants. Now I am going through the second study. It is on the hydrothermal pretreatment to improve resource recovery opportunities. So here hydrothermal treatment exposes the high moisture material to elevated temperatures and pressure. So here basically we worked on these two processes. One is thermal hydrolysis, the another one is STC, hydrothermal carbonization. So they are carried out in the temperature ranges of 120 to 180 degrees centigrade and 180 to 240 degrees centigrade respectively. So when we go for thermal hydrolysis, the purpose is to solubilize the particulates that is present in large amount in the sewage sludge, and then we can go for the anaerobic digestion process, which will give us more biogas yield. Now HTC is at slightly higher temperature it is carried out, and we find two streams here. One is hydrochar, that is solid residue. It can be used as fuel as well as soil conditioner. And the second one, it is liquid stream, which we can again subjected to anaerobic digestion process and also it has some macromolecules which can also be recovered. So I will show in brief that what are our results actually on after this STC on sewage sludge. Advantage is no chemical requirement, no pre-drying step, recovery of useful products. And limitation, it is one of the limitations, energy intensive, but we have actually checked this energy requirements and all, and we found that the temperature during the reaction, if it is of 1 hour reaction, then we can maintain the temperature without heater actually, around 190 to 200 degrees centigrade. So here what we did, this is a graphical abstract.
Last 2 minutes.
Yeah, I will finish in 2 minutes. So this is the graphical abstract. So this is the aeration tank. We found this sludge and then it is centrifuged. So after centrifuged, it contains 8 to 11% solid content and it is subjected to hydrothermal carbonization in high pressure reactor. So we worked at 200 degrees centigrade temperature from 1 to 8 hours. And then this is the process wastewater and this is solid hydrochar. So this has good calorific value but high ash content, but has adsorption properties and it can be used as soil conditioner. And process water, it has humic substances and phosphate, which is a non-renewable resource, it can be recovered out of this. So I will not go through this. Only one thing that I wanted to tell, high calorific value of this hydrochar samples obtained after reaction at 1 hour, 3 hour, 5 hour and 8 hour was approximately 14 megajoule per kg, and it can be used as a co-fuel. But here this high ash content is a problem. High ash content is a problem, but if we actually compare based on these atomic ratios on Venn equivalent diagram, so it is very close to lignite coal. Now this is the another one where we used recovered this humic acid from the liquid fraction for the growth of plant seeds. So we use 3 different types of seeds here. So this is the chickpea, and this is actually this is urad, that is pulse, and this is the millet. So here we used it and we saw no adverse impact of using this humic acid, but it shows the actually it shows the similar result as from the commercial this commercial humic acid that we also purchased. And then we saw this is the growth of plant seeds, and this is the phosphate recovery that we obtained 82% from this is liquid fraction obtained after 1 to 8 hour reaction. And with HA also it is precipitated out, and this is after struvite. So struvite is magnesium ammonium phosphate that is produced, and for this is the specific condition which is used, and we could recover around 77 to 85% phosphate. This is the summary of that. So sewage sludge derived adsorbent showed similar properties and performance of wastewater treatment as that of commercial activated carbon. And using hydrothermal pre-treatment, we can separate easily, which can be used for resource recovery, and it can be used as soil conditioner. So it is one of the major actually field of research where we have to demonstrate, we have to actually study more. And one more thing that I would like to tell in the end, that for this particular process, we are asked to have 2 small scale plants at the sewage treatment plants, running sewage treatment plants based on hydrothermal pre-treatment process to us. And I will like to acknowledge my students who have worked on these topics. So Anirudh Gupta, Milan Malhotra and all, faculty and staff, EACD and IRCC and SAFE. Thank you very much for your attention.